counting pairs with exclusive, or we want the number of index pairs, I less than j such that a sub-I exclusive, or a sub-j is less than capital T. Formally, count pairs I less than j with a sub-I XOR, a sub-j, less than T. We focus on 32-bit integers, so there are only 32-bit positions to consider. Binary viewpoint, less than is decided from the most significant bit down. We compare bits top to bottom. If the highest differing bit of the XOR is 0 while the target has 1, we are smaller. If the XOR has 1 while the target has 0, we are larger. At each bit position, two forces interact: the top-down rule from the target T and the exclusive or relation that says bits differ if and only if exactly one input bit is 1. We can exploit this structure using only 32 steps per number. Method A. Insert numbers into a binary tree, from the most significant bit to the least significant bit. For each new number a sub-j, query how many previously inserted a sub, I produce a sub, I XOR a sub-j, less than T. Then insert a sub-j. This respects I less than j by construction and runs in O of n times 32. Demonstration with 3 bits. Suppose the target T is 101. At a bit where T has 0, we can only follow the same bit branch. At a bit where T has 1, we may add all counts in the opposite branch and continue along the equal branch. This sums all paths that keep the exclusive or strictly less than T. Example: insert two numbers, 010 and 100. Now query for the number 110 with target T equal to 101. We will highlight the equal path and add opposite subtrees when the target bit is 1. Complexity: every query walks at most 32 nodes and adds at most 32 opposite branch counts. Every insert creates or touches at most 32 nodes. That is a constant factor for 32-bit integers. Because we insert only older elements and then count for the current one, I less than j is respected by construction. Method B. An offline divide and conquer on bits. Split numbers by the current bit into zeros and ones. If the target bit is 0, only pairs within the same side can be valid, and we recurse. If the target bit is 1, pairs that cross sides may be valid, and we count them by descending to lower bits on both sides. This also runs in O of n times 32, using stable partitioning by bits. Within counting means we take pairs from the same bucket and go down 1 bit. Cross-counting means we take one element from the 0 bucket and one from the 1 bucket and continue checking the remaining lower bits. We do this bit by bit from the most significant down to 0. Algorithm summary for the offline method. Step 1. Start at bit 31. Step 2. Split by the bit. If the target bit is 0, recurse inside each side. If the target bit is 1, count cross pairs using lower bits and recurse for lower bits. Use stable partitioning or radix passes, so the total work is proportional to n times the number of bits. Both approaches exploit that the width in bits is constant. That yields linear time in n up to small constants. The tree method counts only prior elements to enforce I less than j. The offline bit divide method counts each pair once when the most significant deciding bit is processed. Both are better than n log n comparison-based approaches for 32-bit data. You now have 2 fast bitwise strategies to count pairs with exclusive or less than a target. Use them whenever the bit width is fixed, like 32-bit integers.